We will be discussing a video on how to calculate the fault MVA and the fault current at the consumer premises. It is important to calculate the fault current so that we can calculate the size of earth electrodes and also calculate the specifications of the switchgears to be used. So before we doing this fault level calculations, we have to convert everything in base values. The reason for this is that the transformer's impedance will be different in the secondary and primary for the same load. So in order to make the calculations easier, we have to convert everything in the base value, and the equation used for that is percentage of reactance. Percentage reactance is Ix by V into 100, where I is the full load current and X is the reactance in ohms per phase, and V is the rated voltage. So we will be discussing this equation on the basis of a real life example of a industry which is taking its supply from a nearby substation at a point. The substation is located 0.9 kilometers away from the industry's transformer. The substation has a pre-calculated fault level of 93.4 MVA. Every substation will already have a pre-calculated fault level. Now we have to calculate the fault level at this point and this point, the primary point and secondary point. So in order to calculate this, first we convert this fault MVA into percentage reactance value by assuming a base MVA. So percentage reactance will be base MVA by fault MVA into 100. We assume base MVA is 100. So 100 into 100 by 73.4, we get percentage reactance as 136.23. So at this point, the percentage reactance is 136.23. Now we have to find the percentage reactance of this 0.9 kilometer long cable, add to this, and then we get the percentage reactance at this point, and then reconvert it back into the MVA value. So the percentage impedance of the cable, to calculate the percentage impedance of the cable, first we have to calculate the absolute impedance of the cable, which is given as root of R square plus XL minus XC the whole square, where R is the resistance of the cable, XL is the inductive reactance, and XC is the capacitor reactance of the cable. By doing the calculation, we get it as cable impedance is 0.1357 ohms. Now we have to convert this into the base value, percentage impedance in the base value. So so percentage impedance at base value will be the absolute impedance by base impedance ZB. So base impedance is how we calculate base impedance is just by using understanding the unit of impedance. It is kV square by MVA. Only if it is in this form, it will come as Z, since K square and M gets cancelled, and one B and B gets cancelled, and V by A is equal to Z. So this is the form, kV square by MVA. So kV is the rated voltage, which is in this case 11 kV, 11 square by MVA is already assumed as base MVA is 100 MVA. So Z by 11 square by 100. This 100 goes to the numerator. That is 0.1357 into 100 by 11 square, 11 kV square. And we will have to do another 100 to convert it into percentage value. So it would be 100 into 100 into 0.3157 by 11 square, which gives 11.214 percentage. Now this will be added. This is the percentage impedance of the cable. It will be added to this source impedance to get the impedance at this point. So 136.23 plus 11.214 gives some value here. That is 147.44. Now we can reconvert this value into the initial MVA by doing the calculations in reverse. So initially we did the percentage impedance value was calculated as base MVA by fault MVA into 100. So we do the reverse calculation. Fault MVA will be base MVA 100 by percentage 147.44 into 100. Which gives comes to around 67.82 MVA, but this is too low. We have a minimum standard of at least 150 MVA considering future requirements, so we take this and ignore this. Now converting this back into percentage value for further calculations, we have percentage z equal to base MVA, this same equation, 100 by 150 MVA into 100, which comes around 66. So considering the assumed value, we will get the percentage difference as base MVA 100 by 150 MVA, which is the assumed value into 100, which is it comes around 66.67%. Now we have this is the substation transformer and consumers transformer primary feeding point. Up to this point came up to 66.67% as per the assumed value, and from here we'll have to find out the percentage impedance at this point also. Before that, we can find out the fault current here, which is I equal to 150 MVA by root 3 into V, comes around 7.87 K. That is fault current at this point. This will be used further for earthing calculations. And now we have to add the transformer's percentage impedance to the 66.67 to get the percentage impedance at here. They convert it into fault level and get the fault current at this location. So transformer's impedance is already given in the nameplate as 6.25%. Now we have to convert this into base MVA. So we have to use this equation: percentage impedance of transformer at base MVA by base MVA equal to transformer's impedance by transformer MVA, transformer's percentage impedance. We are converting the base. So this 6.25% is in the transformer's base MVA value, which is 1600 kV, the rated value of the transformer, converted into base MVA. So we use this equation: percentage impedance of the transformer at base MVA value by base MVA equal to transformer percentage impedance by transformer MVA, which is here it is 6.25% divided by 1600. In MVA it will be 1.6. So to get this, we need this. So multiplied by base MVA, which is into 100. So percentage impedance of transformer at base MVA, it will come around 6.25 into 100 divided by 1.6, 390.62. This is the percentage impedance of this transformer. Now this must be added to this point, this 66.67 impedance, and we get the impedance at this output point, which is summation of 66.67 and 390.62 will get 457.28%. And fault level at every side of the transformer, we have to convert this into an fault MVA. So the initial equation which was used, fault MVA, first the initial equation used was percentage impedance is given as base MVA by fault MVA into 100. We do the reverse of this. Fault MVA is base MVA 100 by percentage. This percentage 457.2 into 100. 100 into 100 by 47.8, it will come around 21.86 MVA. This is the fault level at the consumer's feeding point after the consumer's transformer. This gives the fault current. From this we will get the fault current of LTZ as I fault current is take this MVA 21.86 by root 3 into voltage, and we get 29.15 kA. So we got all the necessary data required for the earthing calculation and switchgear selection.